Justin, do you want to start?
Yeah, I'm ready.
Awesome.
Okay, well, thanks very much. I want to start by congratulating the organizers, Khoury, Babette, and Marco, for really putting together a successful school despite the uncertainties and highly challenging circumstances. So this was a tour de force, and I congratulate them. I'm sorry that I cannot be there in person. So as I was preparing these lectures, I was looking back at some of the previous Les Houches summer schools, particularly in cosmology, and I came across one interesting one from 1999. I didn't attend that school. I was a beginning grad student. I guess I could have in principle. But the reason it caught my attention is that I think this really was a pivotal moment in the development of the field. This was just a few months, less than a year after the groundbreaking discovery of cosmic acceleration by the two competing supernova teams. And it was really the dawn of precision cosmology with regards to cosmic microwave background observations, as I'll make clear in the next slide. So it made me think or ponder whether similarly the present summer school may be a pivotal moment in our understanding of dark matter. We'll see. So if you put yourself in the shoes of students in that summer school in 1999, this would have been the cosmic microwave background data that you would have seen. This was mainly COBE data on large scales, and then there were a few ground-based experiments probing anisotropies on smaller angular scales. But really, from that point on, in the next few years, the situation changed pretty dramatically with WMAP, in which the angular resolution of these anisotropies increased tremendously. And of course, here we are today with the Planck, the exquisitely beautiful Planck data, giving us very precise knowledge of the early universe. Now, as you know, the imprint of dark matter, I mean, these temperature anisotropies are pretty much a tracer of the density profile at the time, and the density map. And the imprint of dark matter is throughout these anisotropies. When we look at the power spectrum of these temperature anisotropies, the angular power spectrum, the lambda CDM model provides an exquisite fit, and dark matter is seen, its effects are seen throughout, but there is one particular fingerprint, which is really, a fingerprint of dark matter, which is the third peak. So these are, of course, acoustic oscillations in the baryon photon plasma at the time of last scattering. They're occurring in the presence of gravitational wells that have already been set up by the dark matter. And if there were no dark matter, then you would just see these oscillations that would be damped exponentially by Silk damping. So the fact that the third peak is significant, in fact, it's a little higher than the second peak. Third peak corresponds to the second compression. The fact that it's significant is a sign that there were, at the time, significant gravitational wells already laid out by dark matter. Now, as we know, dark matter is not just important to set out the initial conditions, but subsequently, if we zoom in on a cold region of the sky corresponding to an overdense region at the time of the last scattering, as the universe evolves, you have the Jeans instability kicking in, and as a result, these inhomogeneities begin to grow, and eventually leads to the formation of the first stars and the first galaxies. So dark matter is also critical in helping out this growth of the density perturbations, resulting in the late time matter power spectrum shown here, so the Fourier transform of the 2-point correlation function for the overdensities. And again, lambda CDM provides an exquisite fit. Now, what I want to stress about these observations is that this success of CDM, while it is unquestionably a success, really on those scales, one is not particularly relying on the microphysics of dark matter. In fact, if you open any textbook on cosmology, you'll find that on those scales, you can describe dark matter pretty much as a perfect fluid with negligible pressure and sound speed. So from this point of view, any form of matter that would have negligible sound speed and pressure would do equally well at fitting those observables. So it's the cleanest and perhaps the sharpest evidence for dark matter, I would say. But on the other hand, it doesn't provide us much guidance as to the particular microphysics. There is room in principle for new physics kicking in on smaller scales. Now, as I'm sure you've learned in this school, the true particle physics nature of dark matter really shows up once we start looking at the nonlinear evolution of perturbations. So we usually assumed that the dark matter is WIMPs or axions, basically particles that have negligible interactions among themselves and with ordinary matter. You set up n-body simulations with approximately homogeneous initial conditions. You let it evolve, let gravity do its thing, and the end result is this beautiful cosmic web. You see these filamentary structures, you see these nodes that are presumably host to galaxies in the present-day universe. You see here mergers, clearly by eye. So it's a beautiful system that follows from very simple physics and initial conditions. And so given this, now one can ask, how does this picture of cold dark matter, how does it fit against observations? And as we said, for the cosmic web, you get quite nice agreement. On smaller scales of galaxy clusters, which are the most massive, largest virialized objects in the universe, you also get pretty good agreement with ordinary dark matter. But on scales of galaxies, I think the scorecard is a little bit more murky. Of course, in part, this is due to the fact that on galaxies, the physics is much more complicated, owing to the complex baryonic physics, feedback processes, supernova explosion, gas cooling, etc., which complicates the story. But nevertheless, I want to argue that at least there's something there that at least has motivated my research for the last few years. And that's what I want to discuss next. So if you take galaxies, specifically, I want to think about disk galaxies or rotationally supported galaxies like our Milky Way galaxy. One can look at it from different points of views. There are different observables one can look at. So first of all, if you look at this galaxy, well, you see, first of all, the baryons, ordinary matter in the form of stars and gas. And so you can just measure, in principle, the density profile of ordinary matter. So let me call that rho b. Okay, so as a function of distance, you get a density profile of baryons. And given this profile, you can basically solve Poisson's equation to get what I'm calling the baryonic acceleration. So this is the gravitational acceleration that is due only to ordinary matter. Okay, I'm calling that g bar. On the other hand, from the dynamics of the galaxy, looking at how it rotates, how ordinary matter orbits, one obtains, of course, historically famous flat rotation curves of galaxies shown here. And so just looking at the dynamics, this velocity profile of ordinary matter, you can infer the centripetal acceleration, the dynamical acceleration, which I'm calling the observed acceleration, g observed, simply v squared over r. This is a purely observational statement. In particular, I'm not making any assumptions about dark matter or modified gravity or a combination thereof, okay? So given these two observables, we can plot them against one another. And this is the result from a collection of different galaxies. In a moment, I'm going to show you how this plot is arrived at from observations. For the moment, let's just look at it as an empirical result. So plotted here is this dynamical or observed acceleration on the y-axis. And on the x-axis is the acceleration you expect from baryons only, okay? In particular, the dotted line running along the diagonal, this is the case where the observed acceleration would be the same as the baryonic acceleration, that is to say, no dark matter, no modified gravity, okay? So the fact that you see this trend where at high accelerations, the two agree, okay, that's reasonable. And then where baryons dominate, that's when the two accelerations coincide. But as you move to lower or smaller accelerations, you see that the dynamical acceleration is systematically higher. And that's the, if you want, that's just dark matter or combination with modified gravity, as we'll see. But that's no surprise. You go to lower acceleration and you get dark matter being felt. The surprise, perhaps, as you can see by the plot, is that the relationship between the two is remarkably tight. even by astrophysical standards, it's remarkably tight, okay? It seems that looking at this plot, if I just give you a galaxy, okay, you look at the baryonic distribution, even in galaxies where the baryons are subdominant everywhere, and you can predict, you're just looking at the y-axis, then you read off the value of the corresponding dynamical acceleration, which is presumably owed to the dominant dark matter. Okay, let me see. I think there was a question in the chat. Sorry, maybe Khoury, can you read it? Because I can't see the.
Oh, I just made an announcement about your lecture tomorrow. No question.
Ah, okay.
Yeah.
Okay, no problem. Yeah, and in fact, you can fit a functional form to this behavior, and in particular at low acceleration, remarkably, you find this particular functional form where the dynamical acceleration is the geometric mean of the baryonic acceleration and a characteristic acceleration that I denote by A naught, which is fitted to be of the order of 10 to the minus 8 centimeter per second squared, which intriguingly corresponds to, is of the order of the Hubble constant times the speed of light. Here I've set the speed of light to 1. But that is the story, and I'll just comment that in this relationship, the scatter that you see, or the residuals about this functional form, pretty much can all be accounted for by observational uncertainties. So, which is remarkable because you would expect that there should be significant intrinsic scatter just looking at different types of galaxies. Okay, let me show you how this comes about, how you get this plot. Okay, so here's one particular rotation curve of the galaxy on the left. Okay, so this is a particular high surface brightness galaxy. Let's not get distracted by the different curves. These are the different components of ordinary matter shown here. But the data points are the rotation curve on the left, and these are mapped on the right to particular points in this G observed G bar relationship, okay, if that makes sense. So as you'll see, each galaxy corresponds to a set of data points on the acceleration law, okay? So if you keep going, as you consider other galaxies, oops, sorry. Let me go back one moment. Okay, yeah, now you see other rotation curves, and they begin filling in this mass discrepancy acceleration relation. Okay, so in the end, this will combine 175 galaxies corresponding to 2,600 data points or so.
Could I ask a quick question?
Yes, please.
Thanks. On one of your previous slides, you said that these rotation curves put an upper bound on scattering. What did you mean by that?
So I just mean that it's an upper bound on the intrinsic scatter. So meaning that the residuals about the particular fit. Okay, so if you look at the residuals, there is some error there. So uncertainty of order 0.12 dex. And that can all be accounted for by the error budget of observational uncertainties. So which means that if there is, as you would expect, additionally intrinsic scatter owing to different types of galaxies, etc., it should be less than that observed scatter. Does that make sense?
Is scattering here referring to something statistical or a physical process?
So here it's the observed scatter about the relationship that I showed, right? Here there are various uncertainties associated with this, right? So when you look at these galaxies, they come with different inclinations. You have to correct for that, etc. So there are a bunch of also, there's going to be some uncertainties in the mass to light ratio, which has to be folded in, etc. So ultimately, you can ascribe uncertainties to those, and when you sum them up in quadrature, it accounts for the observed statistical residuals about this mean relation.
Okay, that makes sense. Thank you.
All right, thanks. Very good. So yeah, so this is this relationship, and of course it was, from an empirical point of view, it was in fact predicted nearly 40 years ago now by Mordecai Milgram. This, where, you know, he noticed that rotation curves of galaxies, or rotationally supported galaxies, could be well fitted by this functional form, where the acceleration was approximately given by the baryonic acceleration for accelerations much greater than this characteristic acceleration A naught. But for low acceleration, it would tend to this geometric mean. And he observed that A naught was proportional to the Hubble constant, which hinted at some perhaps cosmological mechanism. Of course, at the time, perhaps unfortunately, Milgram proposed this as an alternative to Newtonian dynamics, so meaning he interpreted this as having no dark matter, and instead that the dynamics of galaxies were determined by a modified law of gravity. I think by nowadays, most cosmologists, the majority of cosmologists, would say that this is perhaps too extreme. As we said earlier, there is clear need for dark matter, looking at the microwave background, large-scale structure, gravitational lensing, etc. But nevertheless, I think if, you know, perhaps, well, one could speculate, but I think if Milgram hadn't pushed this as a true modification to the law of gravity, instead just as a simple empirical law, it would be known as Milgram's law, okay? Much the same way as Tolley-Fisher is an accepted empirical statement. In fact, as an empirical statement, it's unambiguous, and it led Milgram successfully to predict the existence of galaxies that hadn't been observed at the time, namely low surface brightness galaxies. So from my point of view, this is an empirical statement. Even if it's run-of-the-mill CDM in the universe, it has to ultimately, when things shake down, it has to reproduce this relationship somehow. But keeping on with Mond a little bit, yes.
Yeah, sorry, it's a very naive question. What is the index in that A, like A0, A1, etc.?
Yeah, let me go back. Yeah. So here A sub n, yeah, sorry, I flipped a bit the notation, but A sub n is the Newtonian, good old Newtonian acceleration but only from the baryons, okay? A naught is a characteristic acceleration, physical scale, if you want, given by, once you fit the data, approximately 10 to the minus 8 centimeter per second squared.
All right, thanks.
Yeah. Yeah, so if you want, this relationship in the traditional, our traditional sense, would simply hint at how dark matter must conspire to give this kind of kinematical relationship ultimately.
Sorry,
Okay.
can I ask a question? We say that this characteristic acceleration is approximately 1/6 of the Hubble constant, but the Hubble constant has unit of inverse seconds.
Yeah,
not
yeah,
units
sorry,
of
this should be,
acceleration.
it's multiplied by the speed of light, and I set the speed of light to 1, yeah.
Of course, okay, thank you.
But it's intriguing. I mean, you can take different points of view here. If you want to take a more a modified gravity hat, this may suggest that there's some cosmological relation. I mean, it's of course also the acceleration scale you would write down from the dark energy. But if you take a more CDM point of view, well, the Hubble scale is the age of the galaxy roughly, so you know it's not completely surprising that it would appear in the dynamics of dark matter. But anyways, it's an empirical statement ultimately. Yeah, thanks for those nice questions. Huh? Okay, so let's for the moment, for the fun of it, let's just keep going and see. If you wanted to reproduce, forget about dark matter for the moment. If I wanted to reproduce this modified law of gravity, how would I do it with a Lagrangian, okay, with dynamics? So, in fact, this is a problem that Bekenstein and Milgram looked at in the early 80s. And this is how you would do it. So on top of Newtonian gravity, you postulate that there is a scalar field, a scalar cousin to the gravitational potential, which has this funny action, okay, written here. And in particular, what's funny about it, is that it has this funny kinetic term of d phi squared essentially to the 3/2 power. And otherwise, it's coupled to ordinary matter in the same way as gravity, okay? Now, thanks to this nonlinear kinetic structure, if you work out the equation of motion for this scalar, assuming spherical symmetry and static profile, you get this modified Poisson equation, if you want, for the scalar field. You integrate it, again, assuming spherical symmetry. This is what you get, and you therefore obtain this square root relation for the gradient of phi. And therefore, the total force that an ordinary matter particle would experience is the sum of ordinary gravity plus this phi-mediated acceleration, which goes as a geometric mean, okay? So the takeaway message is that it's, in principle, straightforward to write down a scalar Lagrangian that does this trick. Of course, one has to contend with the fact that the kinetic term looks highly unusual with this non-analytic structure. And keep that in mind, because when we discuss in the coming lecture the idea of dark matter superfluidity, we will see that this kind of kinetic structure may not be so crazy from the point of view of dark matter. So indeed, the sort of point of view that I want to invite you to think about is sort of a middle ground or a compromise solution, which is to say that I think unambiguously you can say that dark matter must exist and approximate a cold collisionless fluid on cosmological scales to reproduce the success of the microwave background, power spectrum, etc. But on the other hand, that this empirical law of Milgram, I want to conjecture, originates in new physics associated with dark matter. Specifically, it emerges from new interactions between dark matter and ordinary matter beyond gravity. And the specific context that I want to discuss this with you is the idea that dark matter may be in a superfluid phase in the central regions of galaxies. Now, I want to say, just to set the record straight, that this idea of dark matter superfluidity, I came about it by these galactic scaling relations. But aside from that, even if you said, I don't buy these relationships for whatever reason, I think it's an interesting idea to contemplate the possibility that dark matter may be in a superfluid phase, aside from these motivations. Okay, so I hope I can motivate to you that this is a real possibility, and therefore we should investigate the consequences of that possibility. So superfluidity is probably one of the most striking manifestations of quantum mechanics. You cool down, in particular, let's say liquid helium, as shown here. And when you reach a particular critical temperature, the macroscopic behavior of liquid helium changes dramatically. It no longer behaves as a collection of individual helium atoms, but rather it starts behaving as a coherent whole with collective excitations. Now, you might ask, why should I even think that dark matter could behave in this way? And that's what I want to discuss with you in some more detail to motivate the possibility that this could really be the case. Okay, it's not a crazy thing to fathom. Okay, I'm going to stop sharing my slides. Let me stop for a moment, see if there are any questions. Let's see in the chat room. I guess, okay. Any other questions about the motivational slides?
Yeah, I have one.
Great.
On the slide where you showed the Mond Lagrangian, when you calculated your phi prime, did that mass term have a radial dependence? That M of R?
This M of R here, yes, it does.
So the mass of your scalar depends on its position?
No, sorry. This mass here is the enclosed mass of baryons. So if you integrate this guy over here, you integrate it as usual from a Poisson equation. On the right-hand side, you'll get Gm of R, the enclosed mass, baryonic mass over R squared. And then you take the square root to solve for phi prime. Yeah, sorry, I should have put a B here. This is the baryonic mass, the enclosed baryonic mass.
No worries, that makes sense. Thank you.
Okay, great. Yeah, thanks. Okay, so let me stop sharing this.
Sorry, can I ask a question?
Yeah, please, sorry.
So this strong empirical relation, just for curiosity, could it be explained with the standard picture of dark matter as a cold collisionless fluid? or
You mean
it is in
you say
trouble?
the scaling relations? I didn't hear the beginning.
Yes, this scaling relation involving the square root. Yeah.
Yeah, of course. So yeah, this is an excellent question. So let me go back to share a little bit. Oops, 1 second. Yes, this is an excellent question. Yes, of course. So this is, how should I say? Of course, galactic dynamicists are aware of this, and it's a question that's hotly debated in the community, I would say. Okay, so maybe I can make a couple of comments. So first of all, if you just do simple abundance matching, so here I'm talking purely CDM, okay, you do abundance matching, you find that this trend, let's say, with the scale A naught in it, is roughly reproduced by CDM. Okay, so you do get this sort of overall trend. What tends to happen, on the other hand, is the scatter, particularly at the low acceleration end, tend to be much larger. Okay, so really things start to scatter up in the low acceleration end. And furthermore, the tendency is to overpredict the acceleration, the observed acceleration in that regime. So I think, if you just asked me what, the likelihood that this comes out of CDM, I think, the trend probably is there in CDM, but it's really a question of the scatter. What's puzzling to many, including myself, is that it's such tight scatter, given that there are galaxies that are dark matter dominated throughout, okay, at all radii. And that presumably what ends up leading to this relationship, baryonic feedback must play an important role, and baryonic feedback is stochastic. It's random, depends on the environment. So I think ultimately this is I think this is a fair assessment at the moment. Now there are, of course, also numerical simulations, hydro simulations that try to reproduce the relationship, and there's been a varying degree of success in that regard. Does that answer your question?
Yes. Thanks a lot.
Yeah. I want to give you guys a sort of balanced viewpoint that this is not necessarily, some people would say it's a crisis for CDM. I think the more balanced viewpoint is that if it comes out of CDM with such tight scatter, it remains, I think it remains surprising and deserves inspection. Okay. Is there any other question in the audience? I can't really see.
Yeah, one more.
Okay.
I have to get there.
Thanks. So in your, what is it, like slide 7, early on, I think you were making the point that with lambda CDM, we can describe like the first two items like pretty well.
Yes.
So, I mean, what about galaxies? Like, are you saying that we do not manage to describe galaxies as well with lambda CDM, like the rotation curves and stuff?
Yeah. So, so I think the legally safe words were that I think I said the scorecard is a bit murkier, meaning that CDM does well. Of course, if you take something like the NFW or some modification of NFW due to feedback, it does reasonably well at fitting the rotation curves of galaxies. But I think the point I'm raising is that it's still surprising that you get such a tight relationship between the dynamical properties of rotationally supported galaxies and the observed baryonic distribution. So yeah, I think I would say, I'm trying to be balanced. I think I would say that, CDM, it's not a catastrophe or a major crisis. It does reasonably well, but the name of the game here is that, if there's new physics associated with dark matter, whether it's SIDM or fuzzy dark matter or the stuff I'll talk about, that kind of new physics will show up in galaxies. So where the density is high, etc. So I think it's interesting to consider the possibility of the impact of this new physics and whether it can explain what seem to be conspiracies or coincidences, perhaps from the point of view of CDM.
All right. Thanks for clarifying.
Yeah. Okay. So now let's move on. And I'll go to the iPad. Let's see if I can manage. Okay. Good. Okay. Very good. So I think to start with, to motivate the idea that dark matter may be a superfluid, I first want to review briefly some basic notions in statistical mechanics. In particular, let's start with the phenomenon of Bose-Einstein condensation. Or BEC. So for simplicity, I'm going to consider Bose-Einstein condensate in the case of a free Bose gas, so no interactions. And I'll take this gas to be in thermal and chemical equilibrium with some large reservoir. So that we can describe this with the grand canonical ensemble. So there's going to be associated with this system a temperature that I denote by T, and a chemical potential that I denote by mu, which physically represents the energy required to add one particle to the system. Now, as you all know, in the grand canonical ensemble, the probability that I'm going to call P sub I, the probability of having the system, of finding the system with n sub I particles and energy E sub I, epsilon sub I. So here, to be clear, I'm going to denote epsilon sub I to be the single particle energy. Okay, so in other words, the total energy of the system in that configuration would be Ni times epsilon I. And the corresponding probability to find the system in that state, P sub I with particle number n sub I, is given by 1 over the partition function times the Boltzmann factor, e to the beta n sub I mu minus epsilon I here, where beta is the usual factor of 1 over the Boltzmann constant times temperature, and the partition function z is obtained by summing over all states of e to the beta mu ni minus epsilon I. Oops, sorry, I meant ni outside. Like that. Now, with this partition function in particular, we can calculate the average number of particles, the average occupation number for the given energy state. Let me call that bracket Ni. So the average occupation number in that state is obtained, of course, simply by summing number of particles from 0 to infinity, number of particles weighted by the probability of having those number of particles. And that you can show nicely sums up or gives you a geometric series with exponentials, and you can sum it up. It's a classic textbook result. Is simply given by 1 over e to the beta epsilon I minus mu minus 1. Which is, of course, you recognize as the Bose-Einstein distribution. It's important to keep in mind that this geometric series converges provided that mu, the chemical potential, is less than epsilon I. Okay, and now if I take these average number of particles and I sum over all states, this will of course give me the total number of particles. Which we'll denote by n. So the total number of particles is obtained by summing over all states these average occupation numbers n sub I. So it's simply given by the sum over I of these Bose-Einstein distribution factors. And here what we're going to do for convenience, I'm going to split this sum into two pieces. One will be the ground state piece, and the other will be all the excited state contributions. So I'm going to split this up as follows. So the ground state, which I'm going to assume has zero energy without loss of generality, is simply given by, I just set epsilon to 0 for that guy, so it's given by this factor. So this, I'm saying, is what I'm calling n sub naught, the ground state occupation, where I've set epsilon naught equal to 0 without loss of generality. And then the rest of it are all the excited states. So I naught equal to 0, sum over this Bose-Einstein factor. And this second term I will call nx for excitations. I hope this makes sense so far. Please interrupt if there are any questions. Okay. All right, so now to proceed, it's convenient to define the fugacity of the gas, defined by Z, which is e to the beta mu. Now, you see, oops. Well, first of all, let's note that the ground state occupation in terms of Z takes the very simple form Z divided by 1 minus Z, nicely enough. And now notice that if you go back to this convergence condition, the sum over here, you see converged for mu less than epsilon I, and in particular for the ground state, this means that mu must be negative, you see? So as a result, for convergence of these different occupation numbers, the convention, therefore, is that mu is such that it's negative. It, in principle, ranges from minus infinity to 0. And therefore, for the fugacity goes between 0 and 1. In such a way, of course, that this n naught, therefore, is positive. Okay. Now let's focus a little bit on the excited occupation. Okay.
Could I ask you a question?
Yes, please.
Thanks. Something that I never quite understood in my stat met classes is what fugacity is qualitatively. Can you give us like some feeling? I know that's a hard question, but I could never quite get that.
It's an excellent question. For me, it's just the e to the beta mu. Okay.
Okay. Sure.
Sorry, I don't have a more compelling answer. I think it's just some, no, but it's probably some nice thermo interpretation. But yeah, sorry to disappoint. I would just say it's it's just a simple redefinition of the chemical potential.
Okay, thanks.
Yeah, thanks for the nice question. Now for the excited particles, the excited occupations, what I'm going to do for this guy is it's convenient to then take a continuum limit. Okay, so this system, of course, was at finite volume. That's why we were summing over discrete energy states. But now in the limit that the volume of the box gets very large, we can take an approximate continuous description. And so we're going to take the continuum limit. In which, therefore, the energy eigenvalues epsilon sub I tends to a continuous variable, epsilon, given in terms of a continuous wave vector k in this way. So very nice. We proceed, approximating the sum as an integral. Therefore, we obtain that this sum over I turns into an integral given by the volume of the box, integral over wave numbers, 2 pi cube, of course. And here we have e to the beta epsilon minus mu, where now epsilon is given in terms of k as above. We can, of course, perform the angular integrals. We perform the angular integral, and we're left with an integral over the wave number, k, which I can write in terms of epsilon. So the end result, which you can check in the privacy of your room, is volume times m to the 3 halves, square root of 2, pi squared, and then I'm left with an integral over the energy, the epsilon to the 1 half, e to the beta epsilon minus mu minus 1. Okay, I hope it's clear how I get there. And lastly, we do one more change of variable. Since what we have here is the combination beta epsilon in the denominator, it's convenient to define a variable x, which is beta times epsilon, so the energy in units of kBt. And then this nicely reduces to the volume m to the 3 halves divided by the square root of 2 pi squared. You get a beta to the 3 halves from the measure, and you're left with an integral 0 to infinity over now this dimensionless variable x to the 1 half. Here I write it in terms of fugacity, inverse z, e to the x minus 1. And this integral is a famous Bose integral. It's known as the polylogarithm function, so that in fact you can write this result as the volume, is the volume times this polylogarithm function, g3 halves, which is a function of the fugacity, normalized to the thermal, the Brody wavelength lambda. So let me define these different quantities. So where lambda, thermal, is square root of 2 pi divided by m kBt. Okay, so really it's just the Brody wavelength where the momentum is set by the temperature. So it's known as the thermal de Broglie wavelength. And in general, this g function, which we can generalize its subscript by nu, okay, is defined to be 1 over the gamma function of that nu times this integral, 0 to infinity, the x to the nu minus 1, z to the minus 1, e to the x minus 1. And you can write this as a power series expansion. It's given by, in terms of z plus z squared over 2 nu plus z cubed over 3 to the nu plus ... like so. Okay, in particular, since our variable z ranges from 0 to 1, okay, this function g is monotonically increasing, and so g of 3 halves, I should say here, since 0 less than z, like greater than z, okay, as a result, g3 halves of z must be less than the series, which is g3 halves at 1, okay, and g3 halves at 1 is the series 1 plus 1 over 2 to the nu plus 1 over 3 to the nu, and you recognize this as the zeta function, in this particular case, zeta of 3/2, which numerically, by the way, is approximately 2.6. Okay. So this is the key result when you put it together. So we've computed this number of particles in the excited states. And let me divide by the volume to obtain the number density in the excited states. So I took the number in the excited states divided by volume. We found that this is equal to simply this G3/2 function as a function of the fugacity divided by the thermal de Broglie wavelength to the cube power. And now the key point is, given the inequality established above, this number density must be bounded above by zeta to the 3/2 over the thermal de Broglie wavelength cube. Okay, I hope this makes sense. Let me try to see. Okay, any questions so far? Okay, now this particular fact that the number density is bounded is critical, is crucial, because it means that if at a given temperature, if at some fixed temperature T of interest, you start adding more and more particles to the system, okay, just add more and more particles. Then at some point, the total number of particles may exceed this upper bound, okay? So if at fixed T, you add more and more particles, inevitably, at some point, you will exceed this upper bound. Such that the total number density, total number of particles exceeds this upper bound of zeta of the 3/2 divided by lambda thermal cube. But you cannot put more particles in the excited states than this upper bound, and therefore all the particles you're adding subsequently must all go to the ground state. And this occupation, large occupation of the ground state, is precisely this phenomenon of Bose-Einstein condensation. At fixed temperature, in other words, this Bose-Einstein condensation occurs at a critical number density. So the critical number density at fixed temperature critical number density n sub c is precisely, of course, given by this threshold value of zeta 3/2 divided by thermal de Broglie wavelength cube. But let me write it out explicitly. This is zeta, it's zeta 3/2 times m kBt divided by 2 pi to the 3/2. Okay, so at a given temperature, this is the critical number density. Equivalently, I can, if I think in terms of fixed number of particles, then this gives me a critical temperature below which the system must condense. So alternatively, at fixed number density, we have critical temperature. That critical temperature, Tc, is equal to, so I just invert the above, no? Solving for Tc in terms of n, Tc is 2 pi over mkb times n zeta to the 3/2, all that to the 2/3. So this gives us the critical temperature and the critical number density. Now, the first time you encounter this phenomenon of Bose-Einstein condensation, at least I remember at first, it doesn't sound so surprising in the sense that you take a system, you cool it down, and you say, oh, of course, as I make the temperature lower and lower, particles are going to occupy the ground state. What's the big deal? So I just want to take a moment to give an intuition for why it's actually a huge deal, okay? It's a huge surprise, really a quantum mechanical phenomenon. Meaning you could ask, is this phenomenon simple energetics, okay? Is it just simple energetics? Saying that as I cool a system, of course, you're going to start populating the ground state. It's not so for the following reason. So energetics, microscopically, would tell you, so the microscopic, and you'll see where I'm going with this. So the microscopic criterion, if you want, back of the envelope to start populating the ground state would be to require that the temperature, the energy kBT of the system, a characteristic energy of a particle, should be less than the energy difference between the ground state and the first excited state, epsilon1 minus epsilon naught. Below that temperature, then you really expect to put particles in the ground state. Now, that energy difference, the smallest energy above the ground state, is of course given by the lowest wave vector, the smallest wave vector, which is given by the size of the system. So if you want, this is given by k min squared, the lowest non-zero k for the system, which of course k will be of order 1 over L, the length scale of the system. So this scales as 1 over m L squared, yes, which on the other hand is, actually I put it here, is 1 over m v to the 2/3 in terms of volume, okay? On the other hand, let's contrast this with the Bose-Einstein critical temperature. The BEC occurs when T, or kBT rather, from the above is less than, of course, kBTC. And now you look at the parametric dependence of TC above, and it scales crucially as the number density to the 2/3. Okay, so this is actually this goes as 1 over m number density to the 2/3. And if I write this in terms of total number and volume, this therefore goes as total number of particles to the 2/3 divided by m times v to the 2/3. Okay, does that make sense? So if you compare these two temperatures, you see the macroscopic criterion to populate the ground state is just 1 over v to the 2/3, whereas the criterion for Bose-Einstein condensation is parametrically larger by a factor of n to the 2/3. Okay, so in particular in the thermodynamic limit, the Bose-Einstein critical temperature can stay finite, but the microscopic temperature would go to 0. Does that make sense? So it's a striking phenomenon that at some, from the point of view of microscopics, this is a large finite temperature. All of a sudden you start populating the ground state copiously. Now, there's a beautiful, simple physical interpretation for this phenomenon. The physical interpretation is the following. So we've seen that BEC occurs when the number density of particles, n, exceeds this critical threshold value of zeta 3/2 over thermal de Broglie wavelength cube. And as we said, zeta 3/2 is just a number of order 1. It's 2.6 or so, and the thermal cube. And so what we deduce from this, ignoring this number of order 1, is that Bose-Einstein condensation occurs when the de Broglie wavelength, thermal de Broglie wavelength, is larger than 1 over n to the 1/3, okay? But that is precisely the mean interparticle distance, right? So 1 over density, or 1 over number density to the third is precisely the mean interparticle distance. Let me call that L. So this is a sort of a back of the envelope criterion for condensation, and physically, it's telling us very nicely that my particles, which quantum mechanically have a de Broglie wavelength, will start to condense once the density is high enough that these de Broglie wavelengths start overlapping. Okay, it's a very nice, simple physical criterion. That's when you expect quantum mechanical effects to be important. Okay, this is very nice, but you're probably thinking I didn't sign up for a stat mech summer school. Okay, so what does that have to do with dark matter? Well, it's actually now fun to do a back of the envelope estimate for a necessary condition that dark matter would be in a Bose-Einstein condensate. So let's think about the possibility of Bose-Einstein condensation of dark matter. And for this purpose, we just do a back of the envelope estimate. So I'm going to consider specifically, let's take our galaxy, Milky Way galaxy, surrounded by a dark matter halo. So this is dark matter halo in our galaxy. Okay, and we will ascribe, so of course these dark matter particles are whizzing around in the dark matter halo, and therefore we ascribe a temperature to these dark matter particles given by their velocity dispersion. So the dark matter velocity dispersion sets the characteristic energy scale, which we identify as a temperature, although for the moment I haven't set a criterion to establish thermal equilibrium, but here I'm just thinking of it as the occupation number of different states set by this characteristic energy scale. V is the velocity dispersion now, and therefore the Broglie wavelength of these particles is simply given by 1 over m, is a 1 over mv, no surprise, 1 over momentum. Is there a question? You already just stood up, no?
Yeah, I do have one. Thank you.
Ah, good. Thanks.
Yeah, so for this to work, for dark matter to be in a Bose-Einstein condensate, does it have to be thermally produced?
Oh, yeah, thanks for that wonderful question. So, yeah, I was sort of dancing around that point. Yeah, thanks for making it sharp. So, technically, no, meaning you can have, so in the case, a typical case will be axions. So in the case of axions, what really matters, they're produced out of equilibrium, okay? They remain out of equilibrium forever, as you know, and they're produced predominantly in the ground state from the get-go, and therefore they remain in the ground state forever, okay? And what we're gonna derive here is not incompatible, indeed, with axions. But indeed, what I'm going to have in mind in the case of superfluidity is I will actually want these dark matter particles to be in thermal equilibrium. So there will be a second necessary condition so that their self-interactions are sufficiently strong among themselves to establish thermal equilibrium. I want to make another quick point related to your question because it's a great question. So what's going to be important here, as you'll see, is that these particles are equilibrating among themselves. Okay, so self-interactions have to be strong, but they shouldn't equilibrate with the rest of ordinary matter, okay? Because you'll see they have to be light on the other hand. Does that answer your question?
Yes, it does. Thank you.
Okay, great. Fantastic. Yeah, thank you for this. But for the moment, let's just be agnostic about the thermal properties of this guy. Let's just look at the criterion for condensation. So we have the thermal de Broglie wavelength written here. And as we said, the condition for BEC, the back of the envelope condition to form a Bose-Einstein condensate is that this thermal de Broglie wavelength given by 1 over the momentum should be larger than the mean interparticle separation, 1 over n to the third. And of course, we don't know the number density of dark matter particles, but we know the mass density, or we have a good idea of the mass density. So it's more convenient to write this as the mass of the dark matter particle divided by the mass density of dark matter, all that to the 1/3. Okay, so you see that we get an inequality here involving the mass, the velocity, and the density. And so we can recast this in terms of the mass. You can cast this as a upper bound on the mass, namely that the mass of the dark matter particle has to be less than the mass density of dark matter divided by the velocity dispersion cube, all that to the 1/4. Okay, now we plug in numbers. The mass density of dark matter in our galaxy, roughly speaking, is of the order of, in our local neighborhood, it's about 10 to the minus 25 grams per centimeter cube, give or take, which is in EV. I want to translate everything to EV, ultimately natural units. That's about 4 times 10 to the minus 7 electron volts to the fourth. Meanwhile, the velocity dispersion, well, it's roughly of the order of 100 or so kilometers per second. And in natural units, that's about, in the units of speed of light, that's about 10 to the minus 3 or so. So when you plug that in, you can check that on your own. You plug this into the above, you'll find that the upper bound on the mass of the dark matter particle has to be a few eV or so. So I think for the numbers I'm writing here, it's going to be about 6 electron volts. When you're a little bit more careful about the numbers, you'll find M less than about 3 electron volts or so, more carefully. Okay, but anyways, the main message is clear. If the dark matter is less than EV-ish, okay, such as axions or axion-like particles, then they can form a Bose-Einstein condensate in galaxies. So the key result is that dark matter are, in this case, a Bose-Einstein condensate must be axion-like. Oh, by the way, I want to make a quick point about this. That Bose-Einstein condensation, of course, applies to bosons, but one should keep in mind that the dark matter particles themselves don't have to be fundamentally bosons. Okay, they could be fermions that form bound states. Okay, so that's also important to keep in mind. Basically, like Cooper pairs in superconductors or simply atoms. Okay, so a good example would be dark atoms, as I think Jim Klein will talk about. So they're not necessarily dark matter need not be necessarily fundamentally bosons. Could be bound states of fermions. Okay, we're not done. We can do a little bit more with back of the envelope. We can also calculate or estimate the critical temperature. I think there's a question. When I see Khoury jump up, I stop.
Sorry, I have a basic question. So for so for dark matter to be a BEC, the mass has to be less than 6 eV, and they are axion-like. But how about the other way around? If dark matter is axion-like, do they necessarily have to be BEC, or can they just be like normal?
If they are axion, did you say?
Yeah. As in this case, it's one way, right? If BEC, then axion-like. Then how about the other way around? If axion-like,
I like very much that question. Right? Yeah. No, it doesn't imply because, well, let me in complete generality. Okay, in complete generality, if you had like an axion particle, which has very weak interactions among themselves, if it happens to be produced not in the ground state, but in some excited state, right, then it would never form a Bose-Einstein condensate, right? Now, but the sufficient conditions is that it's sufficiently light, and if it's sufficiently strongly interacting, then it will thermalize, and then you can argue that the temperature will therefore be low enough to form a Bose-Einstein condensate. Does that make sense? So,
oh, yes,
so the sort of the logical thing is if it's just light enough, then it can. Okay, it's necessary but not sufficient. If it's both light and sufficiently strongly interacting, then it will thermalize and therefore Bose-Einstein condense.
Yeah, thank you. I've got another basic question. So,
yes,
like actually, it's way back. Like the way you prove that because the like small n, the number density is bounded from above by the zeta or eta function, then you necessarily have to get a BEC. But do you have some particles that are in the excited state and then some guys are in the ground state?
Yeah. Sorry, I didn't. Can you say the last part again? Do you really have what?
Can you have like some particles in the excited state and then the rest in the ground state? Like, why must they all be in the ground state?
Oh, it's forced upon you by quantum mechanics, if you want. So It's inevitable. So you have a so in fact, what you can show here, I should have said this, but I'll leave you. You can easily now check this in the privacy of your room tonight. That you can show now that from the above basic relations that the number of particles in the ground state relative to the total for the free Bose gas, which we analyzed earlier, is given by 1 minus T over Tc to the 3 halves. This just follows from the above relationships. So what this tells you is that, so first of all, at Tc, or in any case above Tc, the number of particles, this what I'm writing here, of course, is only valid for T less than or equal to Tc. But above Tc, then there are no particles in the ground state. The moment you reach Tc, you start inevitably to populate the ground state. And eventually, as T goes to 0, of course, now all particles populate the ground state.
Ah, okay. So this is
So
a more
it's
formal
it's an
proof.
amazing phenomenon, because at this finite and relatively large temperature, okay, you start having macroscopic occupation of the ground state. It's truly macroscopic manifestation of quantum mechanics.
Okay, cool. Yeah. So this is the proper, the more formal, I guess, way of proving that everything is going to be in the ground state.
So sorry, I can't hear very well.
So this is
say
a
it.
more proper and formal way of proving that every single particle will be in the ground state instead of like bounding it from the above by.
Exactly. Yeah.
Okay, cool.
Exactly. So yeah, exactly. So the logic of the argument is
Okay.
you put an upper bound on how much you can put in the excited states. Therefore, if you continue adding particles, they must inevitably go to the ground state. Exactly.
Okay.
Yeah. Thanks for that. Thanks for that very nice question. Yeah, I'll put this in parentheses and leave for you guys to check tonight. What I was going to get at is you can also calculate.
Oh, sorry, one more here.
Please.
I'm just a little
please.
unclear on that last question. What you
Yeah.
wrote here doesn't look like it guarantees that every particle is in the ground state, correct?
No, that is correct. So,
Okay.
So the relationship shown here, yeah, let's be precise. What it shows is that at T less than Tc, okay, there is some fraction of particles in the ground state, okay? But now, this is very interesting, right? I mean, you can make this more precise and say that in general, this is Ossinger's criterion, that Bose-Einstein condensation occurs when the occupation number in the ground state, okay, is order 1, fraction of order 1 times the total number of particles, okay? And that is really the statement. So the moment you go below Tc, of course, not tuned to Tc, but let's say a fraction of Tc below, then what this tells you above, right, what this guy tells you here is that n naught, the number of particles in the ground state, is some order 1 fraction times n. And that's the key phenomenon. But of course, as you say, as I go to Tc, then that fraction in the ground state inevitably goes to 0.
Thank you.
Thanks. Okay. Yeah. So, okay. Now the next fun thing you can do. By the way, this is really fun to do. Also, check on your own.
I have another question to the axion-like particle. Does this imply somehow the couplings to other particles? Because up to now it sounds more like every boson or scalar boson could do this.
So can you repeat again? There's a little bit of interference. I can't hear very well.
Okay.
Sorry.
I have a question to the that this has to be an axion-like particle. Does this imply somehow something to the couplings to other particles, or can up to now every scalar boson basically do this?
Yeah. So let's see if I'm answering correctly your question. So if I understood correctly, so if you want axions to be the dark matter, of course, as you've learned, inevitably they have to be produced out of equilibrium because they're just way too light, right? They can never be in thermal equilibrium with ordinary matter. So yeah, particles of order eV or so or less, right? In order to be the dominant form of dark matter, they have to be, not coupled to ordinary matter, or if they are, very extremely weakly. Now, with ordinary axions or ultralight dark matter of the type that Lamb will talk about, those particles also have extremely weak self-interactions, and as a result, they don't even thermalize with themselves. So the ultralight dark matter that Lamb will talk about, they form a Bose-Einstein condensate in the sense that in the early universe, they're produced out of equilibrium in the ground state, and they forever remain in that state. okay? On the other hand, the kind of particles that I'm interested in, they actually do have significant self-interactions. Of course, they cannot interact very strongly with ordinary matter for the same reasons, but they can have significant self-interactions, and therefore they can establish their own temperature. I have no idea if I answered your question correctly. I just said a bunch of facts, but does that help?
So, yeah, kind of, but so it can also be other scalar fermions. We can build a model which has not, I mean, how do you define axion-like in this case? Is it just because of the mechanism how to produce them? Or is it, I mean, from which perspective it's axion-like?
Yeah, sorry, maybe Yuri, can you repeat that with the microphone? Because I have trouble hearing the question. Maybe it's I think the room has a bit of echo, maybe.
Yeah, okay, let me try. Are there other scalar particles that would behave like axions and not have self-interactions? Was that the question? No. Oh, the other way around. Okay.
Sorry, I'm a bit unclear, sorry. No, the question was more like, so coming from looking at Lagrangians or something like that, that we can have also scalar particles which are not axion-like. I mean, it seems to be that up to now, every scalar particle can do this, and we don't need to have an axion-like particle. Because,
Thanks. I think, I think I see a little bit what you're getting at. So there is indeed an abuse of language when I say axion-like, okay? Because axion-like can be many things. So I don't necessarily mean that it's a pseudo-Navier-Wilson boson for some broken symmetry like the Fugacity axion so some U1 Pechiquin style. By axion-like, I simply mean that in the spectrum of dark matter particles, right? When you think about the spectrum of dark matter particles, as Jonathan showed in one of his lectures, you have the WIMPs, at the GeV, 10, 100 GeV window. And then once you get to the EV-ish window, you get to candidates that are axion-like. So we know, of course, they cannot be fermions at that light mass scale. So they have to act like bosons. But whether they have to be axion-like specifically, no. They could be. But they have to be bosons, effectively bosons. Okay, does that help? I think, in fact, what I'm going to show, as a matter of fact, may shed some light on this, because when we start describing superfluidity in a moment, you'll see that in fact the description is sort of agnostic. It's an effective description valid at long wavelength and is agnostic to the fundamental properties of dark matter, aside from things like the mass and the self-interactions. Okay.
Okay.
Yes, I think maybe what was a little bit confusing is this abuse of language that we use about axion-like particles.
Yeah. Okay. Thank you.
Yeah. Thanks.
There's more.
Okay.
Sorry, I have a question. All these formulas, they apply only if you have a non-interacting Bose gas.
Very good question. Yeah,
so
correct.
If you have a weakly interacting Bose gas, so the formulas change, because then you really need to do path integral and formalism and so on and so forth. How does this change the constraints on the mass limit, and what changes in general there? Because we have interactions.
Excellent question. So in general, it does make a difference. And what you can show is that even at zero temperature, if you have interactions, the number of particles in the ground state is not, the number of particles that are condensed is not equal to n, total number of particles. Because sort of interactions force particles inevitably to be in the excited states, even at zero temperature. Right. So that's an interesting phenomenon. So what you have to do is really, do the proper calculation, and then there are other approximate methods that one can use, and that's something that we did. I'm happy to comment on this later, but in the case of dark matter superfluidity, there's a way that you can do perturbatively account for the effect of fluctuations onto the condensate wave function. Absolutely, that's a great question. For example, liquid helium is strongly coupled, right? And as a result, there's only of order, I think, 10% or so, maybe 30%, I forget the exact number, of the helium atoms that are in the Bose-Einstein condensate, even at 0 temperature, yet it's completely superfluid. Okay, so that's really interesting question. But then, so in particular, this exponent here, the 3/2 power, does depend on interactions of the particles, and also it depends on the potential. If you put an external potential, so like in the case of an isotropic harmonic trap, you'll get a different power. Okay, yeah, thanks for your question. These are really nice. But I think suffice to say that just to get the back of the envelope story started, as a first pass, this overlapping de Broglie wavelength is a sort of a simple, necessary condition. But
Yeah,
indeed, you have to do the proper thing.
Yeah, because
does that answer?
Yeah. The only thing is that you assume from beginning on that the chemical potential is negative, but for an interaction, so if you include interactions, I think it is more subtle there, because you cannot find stable solutions for negative chemical potential.
We will get there. We will get there. So
okay.
you're correct. The chemical potential at 0 temperature, once you turn on interactions, will become slightly positive. Okay. But we'll get there if I can. Okay, yeah, thanks a lot for those nice questions. I like it. Let me just quickly calculate TC, and then we get to the interesting case that you're looking at, which is the interacting Bose case. Okay. So the critical temperature, again, back of the envelope, you can calculate from the above. I only highlight this because the result is kind of interesting. So you get that, okay, so this is the statement. And once again, we don't know the number density, so we express it in terms of mass density. There you go. So you write it in terms of rho. So I get now m to the 5/3 in the denominator. Then I get rho, zeta to the 3/2. And now you plug in numbers as before, right? You know, you plug in the density, whatever it was, about 4 times 10 to the minus 7 electron volts to the 4th. And now suppose that the mass of the dark matter particle is EV-ish. Okay, so let's put it to be EV. Then you find that this TC happens to be, if I did the math right, it's about 1.8 Kelvin. I think when we did it more carefully in the paper, we found something somewhat lower, closer to millikelvin, but whatever. Anyways, this back of the envelope thing with 1.8 Kelvin is kind of interesting for completely coincidental reasons, that liquid helium has a critical temperature which is 2.17 Kelvin. And if you think about millikelvin, which is what we found more carefully, that corresponds to critical temperatures of cold atom gases. It's just fun. It's pure numerical coincidence. But this is it. Okay, let me see. How am I doing on time? Yeah, how much time do I have? Is it 10 minutes or?
Yeah, I think it's 11, but yeah, order 10.
What's that? Huh?
Order 10 minutes. I think it's 11.
Order
minutes
10 minutes.
Yeah.
Okay. All right. With astrophysical error bars? Okay. Yeah, I'll stop at 10 minutes. Very good. So let's start the discussion of superfluidity. By the way, your questions are great. I don't have a pressure to get to a certain point. So interrupt and we get as far as we can, and that's it. So superfluidity is another striking manifestation of quantum mechanics. What is observed, of course, the salient feature of superfluidity is the frictionless flow of particles. So in this, in our little discussion, what I'm going to do for concreteness is I'll describe superfluidity using a microscopic approach, that is to say field theory. For simplicity, I'm going to work at 0 temperature. And, okay, this is a matter of pedagogy. I'm going to start out with a relativistic theory of superfluidity and then take the non-relativistic limit later. Okay, so start from relativistic. description. And then we'll take the non-relativistic limit later. This is only done, I mean, of course, ultimately with dark matter, we're interested in a non-relativistic superfluid. So it's a bit silly to start from the relativistic perspective, but I only do so because we have more familiarity, perhaps, in field theory with relativistic theory. You might ask why we have more familiarity, and that's because field theory classes tend to be taught by high-energy physicists, not condensed matter physicists. That's the reason. So we'll start with that, and then later on take the non-relativistic limit. Now, but first I want to make perhaps a few motivational remarks for the field theory we were about to write down, okay? So superfluidity, empirically, requires BEC. Okay. Superfluidity means that there's BEC, but not the other way around. You can have BEC without superfluidity, as we'll see. And now the first, and crucially, it requires to have interactions, self-interactions of particles in the system, and we'll assume that those are weak for simplicity. Now, experimentally, superfluidity is observed to be a second-order phase transition. So there's an order parameter associated with this, and you can ask immediately what continuous symmetry is broken in this phase transition. And clearly, since it involves Bose-Einstein condensation, what is condensating here, what is condensating is particles, okay? So you can immediately guess that the conserved quantity associated with the symmetry will be conservation of number of particles, okay? So BEC is condensation of particles. And so you anticipate that the symmetry that is being spontaneously broken, the conserved charge associated with this will be number of particles. And so therefore, symmetry that is spontaneously broken is particle number conservation. Now, in quantum field theory, conservation of particle number is implemented by a global U1 symmetry. So if you want, a working definition of superfluidity is simply that it describes, it's the field theory describing spontaneous symmetry breaking of global U1. So maybe we just put this in our note. Okay, so this seems a bit like a highbrow definition, and how in particular do you get phenomena like frictionless flow out of this definition is very interesting, and that's what we'll see. Okay, but that's our working definition. And by the way, if these particles had electric charge, then the corresponding phenomenon would be superconductivity. So as a side remark, superconductivity is simply the spontaneous breaking of a gauged U1, in other words, ENM. Of course, in the case of a gauged U1, as you know, what really applies is the Higgs mechanism, your photon becomes massive, and that's the broken phase of superconductivity. Okay. So I think given that we're approaching the cutoff, I think it's probably a good place to stop. So next time, tomorrow, that is to say, we will start straight off with the effective theory for this superfluid, work our way down to writing down the effective action for the Goldstone bosons, which are phonons, etc., and then describe dark matter superfluidity. Okay, thanks a lot. See you guys tomorrow. Maybe if there are questions, we have a few minutes. I'm happy to entertain questions.
Other questions? I don't see any. Maybe in the chat. It's also none. Okay. Well, in that case, let's thank Justin, and we'll see you tomorrow.
Recording stopped.